Good morning, here we are again. It's the physics video lecture. Physics 105B video lecture 14. Okay, we've got some great stuff going on. We have left small oscillations and we're talking about gravity of extended objects. And we made our way into Gauss's law. Yeah, so far we have the following. We had G was just equal to the gravitational force divided by M, and we were thinking of a mass here being acted on by some cloud of masses over there that are contained in a volume V with a boundary del V. And obviously it's Newton's law of gravity, so this little mass is being attracted to all of those. And what did we end up with? We had the flux G dot surface normal, the area on the boundary of V was just equal to minus 4 pi times the total mass enclosed. M sub I, I'll just write here enclosed. So we want to get a few applications of this, and the most important one for us is the case of spherically symmetric mass distribution. So this is the total mass enclosed in here, and the example that we're really interested in is if this is a spherically symmetric mass distribution. The mass distribution is spherically symmetric. We're going to go to continuum expression. So this could, of course, be expressed as an integral over the volume. We could possibly do that right now. Minus 4 pi integral density of R prime d volume. Over the volume. We could do that as well. We'd have a mass density. So the mass distribution is spherically symmetric. You guys, I'm sure you've seen this for electric charge, so it is a review, a reminder, but it's interesting to see it here. Good. So the mass is spherically symmetric. So what does that mean? The mass is distributed here in a sphere, we'll say of radius capital R. And as a result, we can say something about the direction of this vector G, okay? Namely, the vector G at the surface. G at the surface. First of all, it's an attractive, right? So it's directed in. And because of the spherical symmetry, it can only be directed towards the center. Okay. The surface must be directed towards the center. The center of the sphere. Now you want to make that clear to yourself, and the way to make it clear to yourself is imagine that vector were not directed towards the center. Okay, so different color here. So we're claiming it's all, every G vector is directed towards the center. Okay, we're here at the surface. If it were not directed towards the center, you could have a you could have a superposition or a vector sum of the part that's directed toward the center and the part that deviates from the center. And that little delta R, delta G, would move as you rotate the sphere. Okay? So by symmetry, it really can only be directed towards or away from the center. In this case, it's attractive, so we know it's towards the center. So it's the symmetry that forces G to be directed towards the center, that requires G to be directed towards the center. Good, now we can do our evaluation. Now this integral G dot n hat d area is going to be an integral. G can only depend on R now, and n hat is pointed outside because it's the outer surface normal, and G is pointed in by this argument. Therefore, the dot product gives you a minus sign. So that's where the minus sign comes from. Okay. And that's a scalar product. You've gotten rid of that dot product there. The dA is just going to give us minus G of R 4 pi R squared for the surface area of a sphere. And this here is minus 4 pi capital M. Oh, there was a G in there, capital G, of course, right? Yes. Let's sneak that in there. Newton's gravitational G. Mg. This was from this flux integral, and this is from the integral above. And we can just see 4 pi's cancel, minus sign cancels. We end up with G of R is equal to Gm over R squared when we divide through. Okay. So this looks just like Newton's law of gravity for a point mass. Equals Newton gravity for a point mass at the origin, which is to say at the center of that sphere. So that's what we set out to prove, that a spherically symmetric mass distribution acts as though it were just a point mass, and we used that last semester for all of our ideas of Kepler problem, planetary orbits, moon, Earth, etc. We were always just treating them as point masses, and here's the proof that one is able to do that. So very important. And okay, so a spherically symmetric mass distribution, attracts like a point mass. Just like a point mass. Now this is for R when R is greater than R. Then it's just like a point mass. So here we are, let's draw this mass, got radius R. So if we're out here at R greater than capital R, and then we could be just skimming the surface, it doesn't matter. We're attracted as though the total mass were concentrated at the center. So that holds true for us as well, standing here on Earth. We're attracted towards the center of the Earth, in as much as it's spherically symmetric. We're attracted towards the center of Earth. And in fact, let me give this cute little example So if you're standing here, we are on Earth, radius r, we can say that our weight on the bathroom scale, that's m times g, is equal to g m over radius of the Earth squared. So that our lowercase g, 9.8 meters per second squared, is actually equal to the gravitational constant mass of Earth divided by the radius of Earth squared. If you've never done it, go ahead and look those numbers up and plug them in and see that they actually give you the famous 9.8. Okay, that's worth it. Okay, so it acts like a point mass when r is greater than the radius of the central body. However, let's go ahead and leave this here. What about when r is less than? Send that up higher. Work. There we go. I'll put that on the homework. That's a famous problem. You may have also done in I know we like to do that one in electricity as well, but homework, find g of r for r less than capital R, and rho equals constant. So we're going to be saying for a uniform mass distribution. That's a famous result. You actually find a linear dependence, and so you're actually going to find a linear dependence, and when you're out at R, then this value should match this one. Okay, so that is a continuous function here. So the g of r is going to look like that if you put them both together. Okay, so that was the first important example. I'm going to do one more, or maybe I'll assign it. So, okay, this was homework, no big deal. This next one I will assign as well. Find g of r for a uniform linear mass distribution. Uniform linear mass distribution. We're not likely to find gravitationally significant linear mass distributions, but this all playing an interesting role, so we want to see that. Find g of r for uniform linear mass distribution. We can say that m is equal to integral lambda d whatever, dz. Okay, so we've got a linear mass distribution along the z-axis, and because it's an uniform infinite linear mass distribution, so it goes out to plus and minus infinity, so for that reason, if I have just some places A and B along it, but I can no longer integrate the whole thing, it's going to have an infinite mass, but I can just go from A to B like that. Mass per unit length times unit length. So that's a certain amount of mass. So here's the thing. By the symmetry argument, you construct what's called a Gaussian surface. Gaussian surface. And because this thing is infinitely long in both directions, there are no components going through the two end caps of this cylinder, but rather you can argue by symmetry that the vectors are perpendicular to the face of the cylinder, and then you use this thing up here. Okay. G dot n hat d area, just for some finite length there, and you'll find the finite length canceling out of both sides. Okay. What happens though is that you get a, can't see this one here, we had a 1 over r squared for this three-dimensional object here, or for the point mass. For the linear distribution, you're going to get a lower power, 1 over r. Yeah, so go ahead and do that one as well. Make sure you're clear on that, because that behavior is also important. If you're approaching a point or receding from a point, you've got 1 over r squared. And if you're approaching or receding from an infinite line, you get a 1 over r dependence. And so yeah, this Rx has to be properly defined. That's the radial part of the cylindrical coordinates. So r is just the distance from the axis. It's not the distance from an origin. Okay? R is the distance from the axis. Good, so you'll get this one. And that's important as well. Good. So the next thing we're going to do is convert all of our expressions to continuous expressions. Continuous mass distribution. Mass distributions. Interesting though, what we did was with point masses, and you can see the program of point mechanics took us this far, right? Took us to Gauss's law. Now this continuous mass distribution is just a generalization where your atoms are so small, there are so many in a given volume that you can treat them, as a continuum. So what we had was this G was F over M. We'll go back to that sum. We had minus G M sub I R sub I, sorry, R minus R sub I divided by r minus r sub I cubed. Okay. And we want to turn this into an integral, because we already had some integral formulas up there. So how do we turn that into an integral? Obviously the sum's going to turn into an integral, and the m's are just going to turn into dm. That's really all we have to do. So we have minus g integral dm, and now the dm has to be referring to the following. We've got r minus r, so instead of a subscript there, I'm just going to give it a prime, and do this. R minus R prime divided by R minus R prime magnitude cubed. Yeah, I'm reminded of what I assigned last time, that you wanted to make the whole Gauss's law thing clear by going through all those steps and the divergence here and so forth. So that's still on table. Okay, and I'm going to put a dm prime here because it means we're integrating at these locations, and R could be inside or outside the body, but R is a fixed point, okay, and we're integrating over the primes. We could also write this minus G integral. We can have a density of R prime, because the density doesn't have to be in D volume. Sometimes I write D3R, I just mean the volume element there. And then R minus R prime, R minus R prime cubed. Okay. Good, so we have the integral form for a continuous mass distribution. When you're remembering these things and when you're constructing things, it's actually better just to write dm first and then, you know, go into this form if you need it, depending on what your coordinates are. Okay, good. We had G there, and I'll include the fact that the total mass is equal to the integral rho of R prime D3 R prime. Yeah, this gets prime, D3 R prime, because we're integrating over the R prime. The volume element. Over the whatever volume we're integrating over. I'll just put a B here, and this defines the mass. Good, so far so good. We now need an expression for the potential. So the thing about these integrals, you know, we just did Gauss's law and did a heroic integral here, but we made use of symmetry. If you actually wanted to do this integral in a general case, you've got 3 integrals to do. So there is a major simplification, and that is, instead of using the gravitational field, you use the gravitational potential. So gravitational potential is next. And that will be V such that the gradient of V, or minus the gradient of V, gives us G. Minus the gradient of V gives us G. And this is not the potential energy, this is potential energy divided by a mass, okay? So we call it the potential, not the potential energy. Of course, we've been calling the potential energy the potential, so you just gotta know what you're talking about. Good. Now this is already staring us in the face because we know that, in fact, I'm just gonna define it. This is V of R is equal to minus G integral dm over R minus R prime to the first power. And this is where some of that vector calculus we did last time comes in, because if you take minus the gradient of V, minus cancels the minus sign there, so you got a plus sign. The derivative, this is M prime, is only with respect to that R, not the R primes, that R. So you get a minus 1 over this denominator squared, and then you've got R minus R prime divided by its magnitude, and you're right back here, okay, with the appropriate minus sign as well. So make sure you understand this rule, because gradient 1 over r minus r prime magnitude, pretty sure we've done this a few times, is equal to minus 1 r minus r prime squared times the unit vector So now we have the potential, and if we can just do this calculation for a mass distribution, you know, and it looks on the surface, it's generally going to be easier than just by taking the derivatives, we can get the fields back. So of course the potential is important to have. Furthermore, we've been through the Lagrangian school, and we know that what we really want is to get the potential and the potential energy in order to find our equations of motion most conveniently. So we've got this potential here, and we know that it's going to be just like a spherically symmetric potential. In other words, we're going to retain what we know about spherically symmetric mass distributions from Gauss's law. Of course, that's going to be true here as well, because we would just take the gradient of this, we'd get the integral, we'd do Gauss's law. So the property, the point mass property of a spherically symmetric mass distribution, of course, still holds. What we want to do now is non-spherically symmetric mass distributions. And there's not much more you can say about them, except that there's the integral for them. Unless they're nearly spherically symmetric, and then we can kind of expand around the point mass. That's the philosophy behind what we're about to do. So our next topic, let's see how much time we have today. Perfect. Okay. So I'm just going to write here next. Non-spherically symmetric mass distributions. Of course, with the Gauss's law, there are a few symmetries that we can deal with. We assigned one on the homework. But we want to look at the general case and see what we can learn. And this is going to be our go-to object here. Actually, let me put this as that note. I had just said it, I'm going to write it down. Under this topic here, spherically symmetric density, then V of R equals minus Gm over R for R greater than capital R. Okay. Just like a point mass if you're outside. So that's your, yeah, good. Just so it's been put in words here. Now we're going to go to some different mass distribution and find its potential. And our goal now is to get an approximation scheme. Okay. So we're doing a non-spherical symmetric mass distribution. What we're going to look at is the following. Suppose we have X and Y axis, and we have a rod here, a thin rod mass, thin massive rod that goes from negative L over 2 to positive L over 2. And we want to know the potential of this thing. And in fact, we're just going to ask, what is the potential of this object at some point X along the X-axis? So find V of X, yeah, V of X, and we're just interested in the one-dimensional case right now, okay? Potential V of X. And for the homework, I'm going to ask you guys to find V of Y. So here we're looking at it on end. There's this rod there. Yeah, it'll be symmetric around here, so we don't have to worry about that. And there you would be along the y-axis somewhere. So how do we find V of X? What we do is use this formalism. It's minus G integral dm over r. So just write that down as a recipe, and then we'll fill in what's going on here. So the dm we can think of as total mass per length times dx, right? That's our dm. And should I give it a prime here as well? I will. dm prime. R is actually just the distance, okay, so we'll fill that in as well. So there's the dm prime, m over L dx prime. And now what are we integrating? We're integrating, since we're just going on the right side here, x minus x prime. So there's an x prime here somewhere. So it's magnitude x minus x prime, but I've constructed it so I don't have any minus signs or absolute values. Anything else? Boundaries of integration. Apparently that's from minus L over 2 to plus L over 2. So now our problem is set up, and you guys are going to do the same thing in the y direction. My integral is easy, yours is going to be tedious, but that's justice for you. Okay, so let's go ahead and do this. V equals minus gm divided by L. So now we have an integral dx prime x minus x prime. So that gives us a negative natural log of x minus x prime. All right, we're integrating with respect to the x prime. Evaluated from negative L over 2 to plus L over 2. That. So we have gm divided by L, natural log, and best to do the quotient there, so we'll have x minus L over 2 divided by x plus L over 2. Good, so there's our exact answer if we didn't make any error. And the next thing, what do we see here? You know, we no longer see anything clearly, so we need to talk about limiting cases. What is the limiting case? Right? We need to find a limiting case so that we can actually believe this thing. So the limiting case I'm interested in is when x is much larger than L. X much greater than L, then we're far away from it. And if we're far enough away from it, its physical behavior should appear to us to be that of a point mass. The same thing as if you're far away on the y-axis, the whole thing should just look like a point mass to you. but we're not seeing any point mass action right here. So we're going to do an expansion. And see what happens. But we're not used to expanding things in a Taylor series for large x, right? We're used to expanding for small x. I'll show a little trick here that you guys are going to like. So we have to do an expansion. We're going to rewrite this, so I'll just say to expand, write v equals gm over L natural log of what's the best way to do this? We want a small quantity x plus L over 2. Natural log of 2. Here's what we do, that's right. I remember. We divide numerator and denominator by x. Okay. And then what we get is 1 minus L over 2x divided by 1 plus L over 2x. Let me scratch my head there for a minute. Okay. So you notice what we've done. We've divided numerator, denominator by x, so that's legit. And now we're going to expand this out. We get gm over L natural log of 1 minus L over 2x minus natural log 1 plus L over 2x. Okay. And notice everything's dimensionless in here now, so we've done a good thing. And recall that natural log of 1 plus z is approximately just equal to z. And if you do that graphically, your natural log of 1 plus z, it looks like this. Okay. And that's just the linear approximation. So you can do your Taylor expansion, of course. You don't have to do it graphically. You can look it up, and then it has some higher terms that are also going to be interesting to us. So, but quickly write this out now. We get equals gm over L minus L over 2x for this one, and minus L over 2x for that one. So we've got a minus sign, gm over L 2L over 2x equals minus gm over x. So that is a satisfying result. So as x is much greater than L, we can say that v of x tends towards minus gm over x, which is the point mass result. The point mass result. Now I'm going to give you guys one more assignment with this interesting problem. The homework is to take natural log of 1 plus z equals z plus something. Take it to third order. Okay, take it to third order and do the expansion here. If you take it to third order, you're going to find v of x equals, we've got the minus g m over x, and then you're going to get something with some constant over x cubed. Okay. This is a really important result because this is the first correction beyond point mass, right? This is just point mass, so if we're far enough away from this object, it's like a point mass. If we go further away from it, or if we come closer to it, it starts to take on a non-point mass aspect, and that's the correction term to the point mass potential. Now that takes us a little bit of work, and not that much though. What you're going to find is, and this is generic, the 1 over x squared term that could be there is going to go away. We're working with, I don't have the general expression. Well, yeah, we're working with the general expression here for finding potentials originally. And we can see that even with a really simple geometry, there's a bit of work involved. This y direction is even more difficult. What we're going to do though, our big plan now, is to find a very general scheme for generating these next terms, in an expansion of the potential in inverse powers, and we're going to do it for three-dimensional objects. So it'll give us a recipe. You got to go through a bit of, it's a little bit hairy to get there, but it'll be a recipe as opposed to every time, right? We've only done for one direction. The y direction's harder. What if we were going off at an angle, right? It would soon just become overwhelming, even for a simple geometry like this, let alone something more complicated. So this is what we're headed for, an expansion scheme in inverse powers for the fully general case. I'll put that down. This is probably a good place. Yeah. So retaining this picture, all I want to do now is write down that potential again and discuss it a bit. By the way, this trick we're going to do in a generalized method as well. This changing, just this trick of dividing here by x and turning, a large x into a small quantity by having it over here will generalize. So next, expanding the potential is going to bring our multivariable Taylor expansions into play. So what we're looking at now, once again, V of R equals minus G dm prime R minus R prime. That's a prime, not a vector. So we're going to be expanding this thing for position for R that is a great distance from an object, okay? And because we have these inverse powers, we get an interesting result. And there's at one point in the calculation, we do a big Taylor series, and there's formally we do this trick that I did right here with the L over 2x. Okay. So yeah, we have a couple problems. I guess that's enough. Did I mention this one as well? So homework for this problem, find V of y along the y-axis And once you get it, there are different ways to do it. If you don't get the integral in closed form, remember we're after the expansion. So formulate it with your your x prime y minus is that distance there from minus L over 2 to plus over 2. And expand your result to obtain v of y approximately minus gm over y, comma, for y much greater than L. Good, that'll be pretty satisfying as well. It's a good set of problems. So next time, we'll kind of declare this done and launch into that more ambitious integration.